How we doing? Let's take a quick look at the benzyme mechanism. Just a reminder, it's a mechanism whereby a halobenzene can be converted into phenol. And remember, this occurs under basic conditions, high temperature, high pressure, kind of a messy gig. Here's how the benzyme mechanism works. The base can grab a proton that is ortho to the chloral group. That would result in that. Which shouldn't feel good. This pair of electrons, they can pop down, and chloride, which we know is a decent leaving group, can leave. That would result in that. Benzyme. Effectively, what's going on here? Give me one word. Elimination. This is just an elimination reaction. This is really brand X elimination. If I had done it all in one step, it'd have been standard E2. That's really all it is. The only thing that makes it weird is that it should be happening with an aromatic compound. That benzyme with that extra bond just doesn't look right. It also shouldn't be aromatic. I don't know what to say. As unappealing as that structure is, the fact is there's evidence for its transitory existence as an intermediate. And we can physically detect its presence. So it's not like we're speculating that this might be how it goes. It does go this way some of the time. So now, once we got this thing, We're still in basic conditions. Followed up with a protonation step. We end up with a hydroxyl group on the aromatic ring instead of the chloro group. The second part of this, from benzyne on, basically is what? Give me one word.
Wait, what was the question?
The second part of this, from benzyne on.
Addition.
Addition. There's an elimination followed by an addition. The overall effect is a substitution. I'm showing the hydroxyl group not on the same carbon that the original chloro group was on. Could it have been?
It's still on the first carbon though.
Yeah, I mean, in this particular case, there'd be no way of knowing.
Yes.
But let's just say, for the sake of,
But yes, because resonance.
let's just say for the sake of grants, let's say we had something on this carbon. Would, still be there, would still be there, would still be there, would still be there. So I started off with a compound where the chloro group was ortho to Z. I ended up with a compound where the hydroxyl group is meta to Z. Did that have to be? Well, look at my benzyne here. I showed hydroxide attacking this carbon. Was there an alternative?
Yeah.
Certainly could have attacked this carbon. These are both the guys that have that extra pi bond. So I could have had my hydroxyl group attacking this carbon. This guy would be the negatively charged one to protonate. In other words, I could have ended up with a hydroxyl group ortho to Z like it was in my starting material. It's basically a 50-50 shot. 50% of the time, we'd expect the hydroxyl group to end up meta to Z in this case. 50% ortho to Z, because it could end up on either of these two carbons. Now, if Z weren't there, we'd have no way of knowing which carbon it ended up on. Contrast that with the SNAR mechanism, which is basically a forced, unlikely, difficult to do, but if you crank up the temperature high enough, you crank up the pressure high enough, you can get essentially just a straightforward nucleophilic substitution. What carbon is the hydroxyl group going to end up on relative to the carbon that the chlorine group was on? Phrased a different way, let's say I got my Z boy here. The chloro is ortho to Z here. The hydroxyl group is going to be ortho to Z autrefois. The hydroxyl group has to be on the same carbon as that the chlorine was on. Nucleophilic substitution. In and out off of the same carbon. But with the benzyme mechanism, it's an elimination giving us a pi bond, extra pi bond, which can be attacked at either end. So there are two carbons, if you will, that the hydroxyl group could end up on if it went via the benzyme mechanism. There's only one carbon that the hydroxyl group could end up on if it went via the SNAR mechanism. And depending upon precise conditions, sometimes you get primarily this, sometimes you get primarily this, sometimes you get a mix of the two. The way you would know, or could know, whether you went primarily this, is if the hydroxyl group ended up on the same carbon as the chlorine primarily. The way you would know, or could know, that it went primarily benzyne, is if the hydroxyl group 50% of the time was on this carbon, 50% of the time was on this carbon. Yes?
Wouldn't it be on the, oh, wait, never mind. Does like, since I know alcohol isn't like an activating group here, but would it favor like the ortho position more just because
Anything that we know about ortho pair activating, med activating is completely irrelevant here. Because that's all about electrophilic substitution. This is a nucleophilic process. Just throw that all out the window. It's a completely irrelevant game to this process.
How would you know if the hydroxyl group was in one position versus the other? Like, how do you know? Basically, how do you know which one is Z?
Well, Z, it's like if there were a methyl group on there.
So you do like something that you know is there.
Yeah,
Okay, I see.
I'm just throwing Z as a placeholder. You know, if we had started with orthochlorotoluene,
I see.
if we had started with orthochlorotoluene, we would end up with metahydroxytoluene and orthohydroxytoluene if we went by the benzyme mechanism. But if we had started off with orthochlorotoluene here, we would get orthohydroxytoluene exclusively. And that's really the only way we know. If it was just chlorobenzene and there weren't some other substituent, so we could see, you know, where chlorine was relative to that, we would have no way of knowing. Okay, I'm done with this unless you tell me I'm not.
so no pair positions with the benzyme, just kind of like in that ortho and meta position.
Yeah, exactly. Wherever, you know, the hydroxyl group is gonna end up on the same carbon as the chlorine, or ortho to that, never meta or para to it. There's no mechanism that would allow for that. And with a benzyne, it can attack either side of the triple bond. Correct. Either side of the pseudo triple bond. Well, alrighty then. Aldehydes and ketones. We know about aldehydes and ketones. We've been talking about aldehydes and ketones since about day 1, 261. And now's our chance to go into them specifically in more detail. Yay! We know what they are, of course. Aldehydes look like this. Ketones look like this. Don't be fooled by this. That's an aldehyde. There's only one way you can put a hydrogen and an oxygen off of that carbon, and that's to doubly bond one of them, and it can't be the hydrogen. So it's an aldehyde. Ketones are often sometimes written like this. You know, don't let that bother you. There's only one way that you can structure that out, and that's to doubly bond that oxygen to the carbon to give everybody their requisite number of bonds. So those bottom two are just kind of lazy ways to write aldehydes and ketones. And they're often done in printed material, because it's easy on any sort of keyboard to do these. You know, you have to go into your special characters to get this. Aldehydes and ketones, mega common, certainly in biology. All the sugars, for example, are either aldehydes or ketones. What's the most common monosaccharide? You all know? Glucose, it's an aldehyde. What's the next most common? Sucrose is a disaccharide. Not that I expect you guys to know this, but fructose is the next most common. It's a ketone. So they're super common all throughout biology. Here's kind of fun. All of you have had this up your nose. In fact, some of you have had this up your nose in our lab. What's that? It wasn't unknown for I forget which lab. This is trans-cinnamaldehyde. And I'm sure I don't have to tell you where this is found. Hello? Cinnamon? It's not the only olfactory compound in cinnamon, but it's the dominant one. It's the principal compound that makes cinnamon smell like cinnamon. This smells like cinnamon. Here's another cool one. This is carbone. Carbone. It's a ketone. How many stereoisomers of carbone are there? How many chirocarbons in this bad boy?
Oh, God, one.
3.
No, that's one.
Others.
One. Wait, no, that's not one. No, there's zero. There's none.
1.
No. Oh, wait, there is one. There's one. I was right. Yeah, one. There's one. Because if you go this way around the ring, it's different versus this way around the ring. So
You know,
there's one.
the other one is 2 hydrogens.
That carbon is chiral. It's got the hydrogen that we're not showing. And yes, 2 ways around the ring, but they're different. And then this mess down here. So there's one stereogenic carbon, which means there's a dextrorotatory version of carbone, and there's a levorotatory version of carbone. The dextrorotatory version, you might know, is spearmint oil. So if you like the smell of spearmint, it's because you like that molecule going up your nose. The levorotatory version is caraway seed oil. if you like the smell of caraway, it's because you like that molecule going up your nose. Here's another in a long list, bazillion long list of the importance of stereochemistry. Spearmint and caraway, I don't know what your nose tells you, but they don't smell at all alike. Very different smells. I happen to like them both, but very different smells, and the only difference between those smells is the three-dimensionality of when that one carbon in this compound. Okay.
I know, I'm like,
A little bit about nomenclature. The simplest possible aldehyde, the one carbon aldehyde. What's UPAC gonna call this sucker? UPAC says what UPAC always says, find the longest continuous carbon chain that contains a functional group. That's obviously one carbon. That would be methane. We drop the E and add the characteristic ending. ON is the ending for ketones.
oh, man.
Different ending for aldehydes, methanal. Is the official UPAC ending for this. And be careful. Don't slur that last syllable, because it might sound like you're saying methanol, a more common compound. So if you intend the aldehyde, methanal, I'm going to emphasize that last syllable to make sure. In writing too, don't be sloppy. A sloppy A can look like an O. Most people, if they're not sure, are going to assume it's an O, because methanol is a more common compound. So you kind of have to be careful to make sure both orally and in writing that you intended A there. In fact, I threw ethanol on a group quiz a bunch of weeks back in here, and half you came out to me and, is that a typo? Because you just assumed I must have meant ethanol. Well, I didn't, I meant ethanol. But your assumption was not unreasonable. And if in doubt, the alcohol was probably what was intended. Okay, so methanol is a UPAC name for this, but nobody calls it methanol. It has a common name, which you all know. This is formaldehyde, yeah. And are we mentioning here where that FORM prefix comes from?
Is that like single carbon?
It indicates a single carbon, and the origin of it. Have any of you spent time in the Southeast? Some of you probably have. Yeah.
Where? Oh.
Yeah, I was on the Gulf Coast of Florida for 6 years. That qualifies in this context. If you've been in the Southeast, you're probably familiar with the fire ant phenomenon. Nasty little red ants. I got nailed by them twice. They're clever little suckers. You're lying around, you don't even know they're on you. And you've got hundreds, if not thousands, on you. And somehow they give the command, ready, set, go. And they all like bite you at once. They've actually been known to kill, although it's rare. Some people have a severe allergic reaction. Most people, like me, just hate life for a while. But as soon as you get them off you, you're back to loving life. But what they inject into you is the one carbon carboxylic acid. Hence, this was called formic acid. Formica, I'm not sure what language it comes from. I want to say Latin, but I'm not 100% sure of that. But it literally means red ant. So this is called formic acid. It literally means red ant acid. It's what those red ants inject into you to make you hate life for a couple minutes. And so as an analogy, it's been extended. Any of the one carbon representatives of any of the functional groups can get the FORM prefix. It's not UPAC. UPAC doesn't have FORM anywhere in its how to name thing Bible. But as a common name, the most common carboxylic acid, it is usually named formic acid. The most common aldehyde, formaldehyde, meaning a one carbon aldehyde named after the red ants. Okay, the two carbon aldehyde, UPAC would say ethanal. Most people in the chemistry pub are going to call it acetaldehyde. The ACET prefix typically means two carbons, with one meaningful exception, which we'll get to shortly. This is also not UPAC, ACET, but very commonly used. There's this, to make a point. 2-chloro?
2-chloro.
2-chloropropanol. Do I ever need a number for the aldehyde functional group? If you're naming it as an aldehyde, you never need to number it because, by definition, it's got to be at the end of the chain. By definition, it's got to be carbon 1. If it wasn't at the end of the chain, they couldn't be an aldehyde. Okay. How about a couple of ketones? What's the one carbon ketone called? Do you think?
Oh my God.
I dug the hole, you fell in. The one carbon ketone?
There's no one carbon.
There is no one carbon ketone. What's a two carbon ketone called? There is no two carbon ketone. The minimum number of carbons for a ketone is 3 carbons, because you have to have the carbonyl and you have to have a carbon on either side. Otherwise, yes, it's an aldehyde. So this is the smallest possible ketone. What would UPAC call this thing? Propanone. 3 carbons is propane, drop the E, add the characteristic ending. The characteristic ending for ketone is ONE. Now you can call that propanone. No one else is going to. It has a common name that you all know. You can't tell me you don't know it, because I know you know it.
What does it start with?
It's possibly the only ketone you'd never heard of before entering an organic chemistry class. Acetone. And here's an example where we use ACET for something that is not a 2-carbon guy. It's not the most egregious abuse of the ACET because there is no 2-carbon guy. So it's not like you can mix it up with some other ketone. There's another way that we often name ketones, very commonly done with simple ketones. The same thing that we did with ethers. The most common way to name simple ethers is simply to name the alkyl group on either side of the oxygen, followed by the word ether. Or with ketones, you can simply name the alkyl groups on either side of the carbonyl, followed by the word ketone. So this would be dimethyl ketone. I have to tell you my true paint supplies in the hardware store story. was a number of years back, there was a, you know, a can that was like labeled like paintbrush cleaner or something. You go to look at the ingredients, it says 100% acetone, which is common and fine. Well, next to it, same company, same size cans, same logo, same everything, just a different color. And instead of paintbrush cleaner, it said something like, I don't know, paint thinner, or something like that. I don't know what exactly it said. And you go to look at the ingredients, it said dimethylketone, which is acetone. So it's the exact same stuff, but they're trying to play on the organic chemical ignorance of the public at large. And say, well, I need some of this. Oh, I need this too. I better buy both cans. Thinking they're buying two different substances, one for this job, one for the other job. And then right next to that was another can, exact same size, same company, exact same logo, different color. And I forget what the title was. I don't know, clean up stuff after painting or something. And you go to the back, ingredients 100%, it just said ketone. Didn't specify, but obviously this was the ketone. So 3 different cans, exact same company, just different titles as to what you're supposed to be using them for, trying to confuse the consumer into thinking they have to buy all 3 cans.
Excedrin does that same thing.
Excuse me?
Excedrin does that same thing. Excedrin migraine, Excedrin extra strength, Excedrin regular is the exact same thing.
Exact stuff. So there are practical value to knowing a little bit of organic nomenclature. Okay. Who's this? Okay, we could go ethyl methyl ketone, que bueno. UPAC would say butanone. Do I have to say 2-butanone?
No.
No. How about this? Pentanone. Do I need a number here?
No, it's assumed one.
Yes, I do. Because 3 pentanone also exists. There's more than 1 pentanone. So there's only 1 butanone. If this were the carbonyl, it would still be this same compound, and if either of these were the carbonyl, it would be an aldehyde. So there's only 1 butanone, so a number is not necessary, but with pentanone and up, the carbonyl could be here or here, which would give the same compound. Here or here would give you an aldehyde, but it could give you here, which would be a ketone that is different from what I have. Okay. So, common names that you should know. You should definitely know formaldehyde. It's like on a quiz or a test, I could say draw formaldehyde. You should definitely know acetaldehyde. You should definitely know acetone. You should be able to use this system. So like, who's this? Yeah, that would be tertiary butyl isopropyl ketone. And you should definitely be able to do the UPAC system. You should also know this one. The simplest aromatic aldehyde, who's that?
Benzol, yeah, no.
This is benzaldehyde. A name that you should know. And here's something else you need to know. With aldehydes and ketones, for that matter, with carboxylic acids, esters, amides, with any carbonyl-containing functional group, carbonyl-containing compound, a very common thing, numerically, this would be carbon 1, this would be carbon 2, 3, 4, 5, and so on. But very frequently, the carbonyl carbon is the carbonyl carbon, The carbon next to that is referred to as the alpha carbon. Next to that, the beta carbon, next to that, the gamma carbon, and so on. The Greek alphabet. So, so UPAC would call this 3-chloropentanal, but you could also call it beta. Pentanal. And the alpha beta stuff is probably used more frequently, not so much in formal nomenclature, but in just talking about a compound. Chemists would be talking to each other and they'd say, in this compound, the chlorine is beta to the carbonyl. Just as a way of describing where the chlorine is. Very, very commonly done. Okay. Physical properties of aldehydes and ketones. Melting points and boiling points, high or low? Okay, that's a little bit of a trick question.
Well, intermolecular forces aren't really that.
You know, in the grand scheme of organic compounds, they tend to be middle-ish. Clearly not as high as, say, alcohols and carboxylic acids, because they're not capable of hydrogen bonding like those guys. Clearly not as low as, hydrocarbons, because, they do have a polar bond, the carbonyl bond, that'd be polar. So they have some polarity. So they're certainly going to have stronger molecular attractions than hydrocarbons. This is going to give them higher melting points, boiling points, water solubility than those things. But they're also clearly not up there with the alcohols and the amines and the carboxylic acids. Middle-ish. Okay, I'm done talking about physical properties. How about, we're all experts in this now. Spectral properties. How about IR? What would you look for in an IR to see if you had an aldehyde or a ketone? Yeah, the big thing is you look for evidence of the carbonyl bond. Where would you look for that evidence?
17.
Around 1700 wave numbers. If you find a nice strong sharp peak in the 1700 wave number range, does that tell you you have an aldehyde or a ketone?
You have a carbon.
Yeah, all it tells you, IR just gives you bonds. All it tells you is to have this bond. It could be an aldehyde, could be a ketone, could be carboxylic acid, could be an ester, could be an amide, could be an acid anhydride, could be some other things we haven't talked about. Lots of things have carbonyls. So it's very useful, but it's not all that specific to any given functional group. Its absence is great stuff too. Tells you you don't have a carbonyl. That eliminates all sorts of functional groups. Not much else we can say about IR. How about NMR?
Nope.
No, one,
Well, keeping aldehyde.
Would it be like
One.
middle of field? No split.
Yeah, I mean, the alpha hydrogens are going to be somewhat downfield. Because of their proximity to the highly electronegative oxygen atom. And the beta guys a little downfield, but not as much as the alphas, and so on. And then a huge thing you'd be looking for.
no splitting? Well, never mind. It is not the one.
Like a way more upfield hydrogen.
Down and around.
The way more who field?
Up, downfield, yeah, that one.
For who specifically?
The hydrogen attached to the carbon.
Exactly. If you have an aldehyde, this guy is way downfield. And he's typically down around 9. The only other thing that you typically find down that far are carboxylic acid hydrogens, which are on average even further downfield than aldehydes. And if you see something 9 or greater, it's going to be an aldehyde or a carboxylic acid almost all the time. So that is quite helpful. Okay, 8 minutes left. Preparation of aldehydes and ketones. In other words, how do we make them? How do we synthesize them? I'm going to give you, what, 5 methods, I think. I'm going to give you 5 methods. One does involve a Grignard, actually. None of the 5 methods are totally new. A couple of them are going to be absolutely not new in the slightest little bit. And 3 of them are going to have some twists. Generally speaking, Grignards are not a good way to make aldehydes and ketones. Grignards react with aldehydes and ketones to make alcohols. What is one good way to make aldehydes and ketones we've talked about?
Oxidation.
Oxidizing who?
Alcohols.
Alcohols. Exactly. More specifically, who do you oxidize to get an aldehyde? A primary alcohol. You take a primary alcohol, you can oxidize that to an aldehyde. Who are you using?
No, not
No,
PCC.
Yeah. I don't necessarily care that you remember PCC, but it is important that you appreciate that normally oxidizing a primary alcohol is going to go all the way to a carboxylic acid. So if you want to stop at the aldehyde, you need some sort of special reagent like PCC. Who do you oxidize to get a ketone? A secondary alcohol. Any of the standards will do there, as far as oxidizing agents. In which you get an aldehyde or a ketone if you oxidize a tertiary alcohol. Yeah. Trick question, nothing. Tertiary alcohols are non-oxidizable. So there you go. Nothing new there. You've already known how to synthesize aldehydes and ketones.
Reducing carboxylic acid or esters. Oh wait, yes,
Yeah.
yeah.
Here's another method that absolutely not new. Ozonolysis of alkenes. You guys remember this? Two-step process, ozone, followed by, it forms what's called an ozonide, and they have to disrupt the ozonide. Don't worry about step 2 here, because all sorts of different reagents can be used. But ozone is always a part of all ozonolysis reactions. And we all remember, he says optimistically, we simply cleave at the pi bond, and those two carbons are now doubly bonded oxygen, creating aldehydes and ketones. You'll get an aldehyde or ketone depending upon what may or may not have been bonded to the original sp2 hybridized carbons. Give you one more today. One that is absolutely not new. Let's see if you can come up with this one. Suppose you wanted an aromatic ketone.
Salt.
Anyone has a class memory that goes back, I don't know,
Salt.
maybe as far as 3 days.
Salt. Sulfonate.
Maybe 20 seconds and I can sit here and wait.
I totally forgot what we
Freedom capsule?
There you go. Not alkylation, that won't do it. Acylation, exactly. Friedel cross acylation results in an aromatic ketone. The aromatic compound reacted with an acyl halide. In the presence of a Lewis acid catalyst, you get acylation of the aromatic ring, which results in a ketone. So there's 3 ways to synthesize ketones that involve absolutely nothing new. Yeah, you got 11 seconds. What to do, what to